Hi everyone, I'm Usman Ali and we'll talk about the cryogenic hydrogen energy system LEAD project number 5. And we have industry partners, BOC and Westington Cryogenics in this project. And we talk about the scope and innovation of this project, what we are going to do and what we have achieved in far and what our plans in the future for this project. The main innovation of this project is the liquefaction of hydrogen, and we are developing a small-scale liquefier for a small-scale airport application. And the capacity of this small-scale liquefaction is 0.5 tons. And in addition, we are also working on the design of a small-scale jewel for the storage of liquid hydrogen. And we are also looking into the safety aspects of transporting or loading and unloading liquid hydrogen from one device to the other device, and what kind of losses happens when we transport liquid hydrogen from one vessel to the other vessel. In addition, we are also looking towards this supply chain of the liquid hydrogen for the small-scale airport application. That what happens if we liquefy hydrogen at the airport and transport it towards from one device to the other device to the airplane. So what kind of process happens, what are the safety implications, and how we can manage it, and what are the supply chain issues within the airport actually for liquid hydrogen. So this is all about what the scope is. The first work package is towards defining the thermodynamic package or thermodynamic models for the small scale liquefaction of the hydrogen. Second work package, we are concentrating on the design of a small scale vessel for the storage of liquid hydrogen. And third is how we are managing those losses of liquid hydrogen when we transport liquid hydrogen from one vessel to the other vessel. And how can we minimize those losses? And what are the safety implications with respect to this application for the airport? So at the moment, we all know that liquid hydrogen has more energy density in comparison to a gaseous hydrogen. And we know that it gets liquefied at minus 253 degrees centigrade. That's the most cryogenic conditions that we have to achieve, 20 K. And we are going beyond that, and we are developing a model for subcooled liquid hydrogen. Instead of saturated conditions, instead of just liquefying it, we are subcooling it so that we can have a stable condition of liquid hydrogen during storage. In addition, we all know that during liquefaction, there are different isomers of hydrogen, ortho and para, and we have to work across those isomers too, so that we have a stable form of hydrogen as a para hydrogen, which should be 96% the storage conditions. And doing so, a lot of energy is required to achieve that cryogenic conditions, and theoretical amount of energy is 2.7 kilowatt hour per kilogram of liquid hydrogen. And our energy in real conditions are much higher, and we are trying to reduce that energy requirements for the system by defining different thermodynamic models for liquefier of that small capacity. And what literature told us about that for small-scale liquefaction of hydrogen, we generally use helium Brayton cycle. That's a thermodynamic term, that how different units in a plant are combined together so that we can attain the liquefaction of hydrogen. And we are working by playing with those units so that we can develop a mixed refrigerant cycle or a different cycle so that our energy requirements are reduced for the system. So in doing so, we are doing the modeling work using process simulation tools of the chemical engineering, S1 HICE and S1 Plus, and we are doing some assumptions for the minimum temperature approach for the heat exchangers for the cold boxes in our systems, which is 1 to 2 degrees centigrade, and the efficiencies for moving parts are 80%, and pressure drop is 10 kilopascal for the system. We are assuming there are no heat losses at the moment. With the environment, the system is adiabatic, so that we can first do the things and then check it with the real system, and then we can play with the numbers. So this is the first model that we have generated until now, which is a helium Brayton cycle, in which we are using helium as a refrigerant, and we have different colored boxes, which are cold boxes where helium is liquefying the hydrogen by interacting the heat transfer to the system. And in a heat exchanger, we generally have to constrain our system by the temperature approach, by difference in temperature of cold and hot steam. And we are playing with these numbers so that we can achieve lower amount of energy in our system. Our capacity is same for the system, which is 0.5 tons per day, which is similar to capacity of a small scale airport. And we are maintaining the hydrogen with para percentage of 96% and the pressure of liquid hydrogen to be 1.2 to 1.5 bar. And we are also examining a different system in which we are using nitrogen as a pre-cooling component and then putting helium as a refrigerant utility, and in which the number of units are reduced. We are having two utilities, helium and nitrogen, and we are looking at how this will reduce our energy requirement for the system. So far, we got some good results with these two cycles, and if you see with respect to the first two numbers, which are the flow rates of our cooling utilities, helium and nitrogen. In the first cycle, where only helium was there, we are only using helium. However, the inventory is increased for the second cycle, but if you see the last two numbers, which is net power requirement, is reduced when we used mixed refrigerants like nitrogen and helium. And also, our specific energy requirement is reduced manifold from 21 to 17 kilowatt hour for 1 kg of liquid hydrogen liquefaction. That's a massive decrease when we are moving towards the other number of cycles, other number of refrigerants. So we are actually looking for other mixed refrigerants and trying to model them and see that how much lower this specific energy consumption we can attain for the system. In addition, we are also designing a small-scale jeweler for the liquid hydrogen, and there is a very limited literature about that what the design strategy and what the design methodologies are available. The available literature is only about the saturated liquid, which is just at the liquid state, not a subcooled liquid. So if we see about the literature, there is vapor density multi-layer insulation system for the design of a vessel, or a vapor cooled shield systems, but there is no literature about subcooled liquid hydrogen storage systems. And we are actually trying to advance that literature so that we can design a vessel, a small scale one, for storage of a subcooled liquid hydrogen. This is those terms actually dictate us. The first one is, which is VDMLI, where we have multi-layer insulation systems of different polymers and different insulators which are available in the system. The second is in which we transport or we move our boil of gas, the vapor which are generated from the liquid hydrogen in the system because of any reason, because of temperature gradient and other aspects, are moved towards the annulus region of our storage device, so that it can shield with respect to the environment and can reduce the heat transfer effects, and we can have a better, more liquid at the state in our storage vessel. So far, we have done what kind of models are available in literature, and we are moving towards that how we can advance it towards subcooled liquid, and hopefully in later stages we can come up with some good results with respect to that storage device. The third item which we are looking is that how losses happens when we transport liquid from one vessel to the other in case of liquid hydrogen. There are multiple kind of losses that are being reported in the literature. One is because of the pressure difference between the two vessels, or because of the density difference between the two vessels. One vessel has a liquid which has a different composition, different temperature, different pressure, because of which the density difference between the devices, and if we move liquid from one vessel to the other vessel, the losses might happen, and the liquid may vaporize it. There may be a rollover because of the density differences in the system. there may be a pump that you heard in the first presentation, that what kind of pump should we use when we transport liquid from one vessel to the other vessel, and how this pump will behave, and what would be the line containment in the liquid hydrogen, which is now being transported towards the next vessel, or loaded or unloading is being done, or what is the losses which might happen during the moving machinery, which generate heats during its working, because of which liquid hydrogen may be lost. And the important aspect is the temperature gradient between the liquid hydrogen and the environment. That's the main aspect, because liquid hydrogen is liquid at the 20 K, and our environment is 25 degrees C. So that's a major temperature gradient, because of which liquid hydrogen get vaporized easily. We do not get the same amount that we are trusted to get. And we are also looking what kind of safety implications will be there, especially with respect to application for the airport. And we will be doing through some techniques that we generally use for our safety analysis, in terms of getting responses from our project partners and the people, experts in these areas, so that we should know what kind of factors should we consider, and then we rate them, and then we consider that how these safety implications will play when we consider liquid hydrogen as a supply chain in a small scale airport application. And in future, hopefully we will come up with some more models for liquid hydrogen for using mixed refrigerants or cascading of refrigerants, that how we can minimize the specific energy consumption, the design of 250 liter of liquid hydrogen storage vessel, and the safety implications of liquid hydrogen for a small scale airport. That's all from myself.